Good afternoon, all. So, it is a great pleasure for Department of IT of Sri Vishnu Engineering College for Women to welcome all the participants to the fifth day of 2-week online FDP Data Science using Python. So, I am pretty much excited to introduce our guest speaker today, Dr. Sri Vallabha Devi, who is going to talk about machine learning for large datasets. So, before starting the session, let us have a quick introduction about our guest speaker. Dr. Sri Vallabha Devi is a lead data scientist with Tiger Analytics. As a part of his role, he leads teams solving business problems in various industries like retail, transportation.
Hello, madam.
Uh, can you hear me, sir?
Yeah, sir. Yes, sir. I think a problem
Madam,
with the
yes,
madam connection.
no problem.
Just a minute, sir.
Sorry,
Again, okay. Yeah, oh, no
sorry,
problem.
sir. I have
Okay,
issue
okay,
with
madam.
my
Please continue.
network.
Please continue.
Yeah. So he is a lead data scientist with Tiger Analytics. As a part of his role, he leads teams in solving business problems in various industries like retail, transportation, and manufacturing. In past projects at Tiger Analytics, he worked on developing deep learning models for video analytics and machine learning models for anomaly detection and price prediction. His current projects were focused on recommendation systems and natural language processing. Prior to this, he worked as postdoc fellow at IIT Madras in statistical analysis of liquid sprays. His doctoral thesis was on large eddy simulation of sprays, a branch of computational fluid dynamics. His areas of expertise are machine learning, statistical analysis, reduced order modeling, and simulation of physical systems and scientific computing. He holds his BTech in Mechanical Engineering from IIT Madras and PhD in Aerospace Engineering from Indian Institute of Science, Bangalore. So I ensure that the session will be quite profitable for all the listeners. So once again, I welcome you, sir, on the behalf of all. Session is over to you, sir.
Yeah, thank you very much, madam. So we'll get started, and I think it is a relaxed session. So please feel free to stop me in case you have any doubts. You need not wait till the end of the session. You can raise hand in between or ask. That is not a problem for me. So we will talk about machine learning on large data sets. So when we say large data sets, we are not referring to data that is like say 1 GB or 2 GB, but data that is of the order of terabytes. This is data that sits on a company's database, which cannot easily be replicated, or you cannot make your own local copy and then build a model on it. So in the context of large data, many problems can be solved, but we will look at one class of problems called the recommendation systems. So this is what I'll be talking about on the topic today, on the large data sets that we are referring to today. So this is the outline of my talk. There will be a brief introduction. We'll go to simple recommender systems and then go to data-driven approaches, and finally talk about some advanced concepts. Even though it is about recommendation systems, I wanted to keep it generic so that we start from a very basic approach and then build up in the terms of complexity. So that is how it will be. So we'll take the case of an online retailer. All of us must have bought at least something during the Dasara or Diwali sale on Amazon, right? So Amazon is a well-known online retailer. We will just look at their scale. Although everybody need not be as big as Amazon, just to understand what is the complexity when we are referring to large data, let us look at the statistics for Amazon. So worldwide, around the world, Amazon has 150 million Prime customers. So there are people who are also not members of Amazon Prime. That number can be 2 times or 3 times of this number. But a very good estimate is that Prime customers are a reliable metric for Amazon's customers, and there are 150 million people. So it is like 15 crores in the Indian context, if you think of it in terms of crores. And they sell about 12 million products. 1.2 crore products are what they sell worldwide. And one other metric says every month around 197 million people buy electronics. It can be phones, tablets, computers, or electronic equipment, whatever it is. Every month people buy this. Now the numbers are not the numbers as such are big enough. But to think of it in the terms of real complexity, just imagine one scenario. Every customer in the 150 million customers can buy any of the 12 million products. So if you multiply these two numbers, that is the possibilities that Amazon is looking at. And if you again dig deeper, all the products that Amazon sells are not one-time purchases. Meaning, if it is a mobile phone, it is a one-time purchase for a customer in at least 2 or 3 years. But if you think of daily goods like eatables or food items or clothes or something, people buy them more frequently. So every customer in the 150 million can potentially buy any one of the 12 million products and then can also buy it repeatedly. So the number or the complexity or the probability that we want to look at is 150 million multiplied by 12 million multiplied by some number, which is the frequency of the product. Those many numbers are what we are trying to estimate in any context. If you want to say whether so and so person is likely to buy this product, when you want to estimate that, you also have to want to have an estimate for all the products that are involved. So we will see how we build a machine learning model to guess or to suggest what a customer is likely to buy. Now, this is what we look at from outside, but inside Amazon, even though they have so many customers, so many products, they do a reasonably good job of recommendations, right? So most of us must have seen recommendations that Amazon makes. We will see how they arrive at those recommendations. Suppose you buy one item on Amazon, how do they come up with other items that they will suggest to you? And if those other items are random, then they will never get it right because they have a lot of products which they can randomly show. So think of it like if you open Amazon once a week, and every time they have an opportunity to show you 3 recommendations on their mobile phone, and they are guessing the recommendations randomly. They have around 12 million products. If you think of it at a country level, let us say even if it is 1 million products, there is a very less chance that they will get it right every time, or at least once in 1,000 attempts. There is a very bleak chance that they will get it right if they show it randomly. So there is some logic or some calculation that Amazon will do before they show us any recommendations. So how do they come up with those recommendations is what will be the topic or the topic of this presentation. We will try to understand how you can get to know more about your customers and about your items. When you sell a lot of products and lot of customers are there, how do you build an understanding? That is what we will see today. So recommender systems are basically two types. One is a simple recommendation with less data or really no data. That is some simple recommendation systems that we will see. Then the other class is data driven, where you have data about the products, you have data about the customers. So you know your customers because they log into your website, and then you also know about the products because you have a description of the products and the class and category of the products. So that is another approach of data driven recommendations, which is what companies at scale do. Companies which have a lot of customers, lot of products do data driven recommendations. That will be the main topic. But for the sake of completeness, we will also look at what other things, other kind of recommendations exist. And then challenges. The challenges to solving any recommendation problems. So data sparsity, how much time does it take, and how do we evaluate? These are the typical challenges that any data scientist would face when they go on to build a recommendation engine. We will see how they work. So what are conventional recommendations? Suppose we know nothing about a place, or what do people typically recommend? So I don't know how many of you are from the same place as your college, Bhimavaram, but if anybody goes to Godavari districts, they typically recommend a sweet called Potareku. That is a sweet traditionally traditionally made by people there, and is very popular in the Telugu states. So when people go there, the simplest recommendation we make are the popular items. What is most popular in that place? Or we do geographical indicators. You go to a place of historical importance, you tell them, okay, this is the place you can go and see. Or about movies or music, it will be about personal preference. When your friends suggest some books to you, or some movies to you, or some say songs or something, that is based on their preference, and because he or she is your friend and your tastes might match, you might also like it. These are what people will do typically when they say, oh, what do you recommend? If I go there, what do you recommend to do? These kinds of things are very conventional. All of us would have seen them at some point or the other. Now, if you take away that personal connect of friends and you look at people where you know nothing about the customer, there's a shopkeeper or a store owner, he knows nothing about the customer. How does recommendations happen? So that is what we will see now in a simple recommendation context. So think of a simple food truck. Food trucks are popular in big cities where people bring a truck, park it somewhere, and make food items, eatable snacks or evening snacks or breakfast items and all, and sell. Now, let us say there is a food truck and you are the owner of the food truck. A new customer comes to you and they will ask you, what do you suggest that I eat? You know nothing about the new customer. You don't know whether the new customer will like, in the simple context of say idli and dosa, you don't know whether the new customer likes idli or dislikes idli. But what do you do when you know nothing about the customer? You will suggest the more popular product that you sell. So you are the owner of the food truck and you know that idli is the most sold product any time of the day or any time of the year. Idlis are more popular than anything else. You will say, okay, people eat idlis here, so you can taste idli. That is what you will do. Yes, sir. Any doubt, sir? Hello?
No, sir. You can go ahead.
Yeah. Sorry, I thought somebody wanted to ask. Okay. Yeah. So when you don't know anything about the customer, you suggest what is most popular in your store. That is what we will do. And at most, what you do, you may account for seasonal variation. By that we mean in summer, some things are popular. In winter, some things are popular. Say the same food truck sells juices and tea and coffee. In summer, you would suggest juices, whereas in winter, you will suggest tea or coffee. That kind of thing you can account for. So this works very well when all the products are equivalent. By equivalent, we mean when a customer comes to a food truck, they are coming to eat and satisfy their hunger. So idli or dosa are equivalent. They will they'll serve the purpose of fulfilling the customer's hunger. That is all it will do. So in such kinds of systems, it is very easy. You don't need to know much about the customer. You can suggest a popular item and be comfortable that the customer will taste. Now, taking it to a slightly more detailed level, you don't know much about the customer, but you may know about what they buy. Think of it like a supermarket, more or big bazaar or whatever supermarket that you visit. When you go and buy items, they do a bill on the computer. So the computerized billing will help them list out all the items that are sold in a particular bill. So you go, you buy a set of items, they bill for you, and then in the database, all these items are saved. Then what do? They don't know about the customer unless you give your phone number or unless you give your take a loyalty card from them. They don't know who you are, but they know what you buy. So from all the bills that are processed in a supermarket, the store or the shop owner can easily identify what are the most common products that go together. Meaning, think of it like say cool drinks or chips or bread and jam. People who buy bread in a supermarket are most likely to buy jam also because bread and jam are very popular items in the supermarket. So this is how the supermarket works. Now,
Sir, your voice is not audible, sir. Please unmute, sir.
it has gone on
Yeah,
mute.
yeah, yeah.
Sorry. Yeah. Okay. So what do we do now? What can we do when you don't know about the customers, but you know about the products that they buy? You can give offers on those products put together, saying that if you buy bread, I will give jam for 5% off, or buy jam and bread is 10% off, or you can say combo pack. So this is the second case where you don't know about the customer fully, but you know about the products. So here the products are not equivalent. They come to you and say, I want to buy bread. You can't tell them, okay, buy a biscuit packet or buy cool drinks. They are not equivalent. These are different purposes. So in such cases, market basket analysis is what it is typically called. In market basket analysis, we look at most common products and give offers on both of them put together. So this will help in driving the sales. If you want to push the sales, this will help you pushing the sales. Now, the third category is where it is mostly online sales. If it is online sales, you know the product, you know the customer, because the customer logs in through a chat, logs in through a account. You know the customer, you know what they do because they log in from the same account. if you have an app and if the customer has installed your app on the phone, you know even more data about the customer. So for an online store, let us say there is a kids store, customer comes and buys some kids child's clothing. This is what they buy. Let us say they buy some shirts and some pullovers or whatever you call it. Then you know that there are kids in their home, so you can suggest the next popular items or next items that customers are likely to buy. So when they buy child's clothing, you are very sure that there are small kids, either small boys or girls in their house. So you suggest items which are suitable for boys or girls of that age group. So a milk bottle or a water bottle or some toys which are relevant for that age group. This is what you will buy or you will suggest. So in this case, you know something about the customer. You know that the customer will buy items of this type. Now let us say the customer buys say something like a football. Then you know that the kids are not very small. They are not infants. There are kids who are like 5 years old or higher, because 5-year-old kids can run and play football. So you suggest toys which are suitable for their age group and not water bottles or milk bottles. So this is the case where you know something about the customer, because you have customers logging into your database and they also have an account, so you can track the customer. You can track them from sale to sale. The customer bought something with me last year. He has logged in today again. I know what is it that he may buy now. I can estimate that if they had a kid 1 year ago, the kid will be 1 year old now. I know that instead of selling small diapers, I will pitch medium-sized diapers to the customer. This is what we can do. So these are the three basic levels of recommendation systems. The first one is where you know nothing about the customer. The second one is you don't know about the customer, but you know about the products. And the third one is you know both. You know about the customer and you know about the products as well. Now, these are all easy to form rules, because the products they have a relation between the products. But what do we do if you go to a different category of retailers or stores? Say you go to Amazon and somebody comes and buys some book on Amazon. They buy some book. So what do you know? Can you know that they have kids, or can you know that they like reading books, or can you know that they like that particular author? You know nothing, because the variety of products you sell on Amazon is too much, is very high. You can't really pinpoint what the customer will buy next. In simple terms, there is no logical relation between different products that you have in your database. Or even though there is a logical relation, you don't know much about the customer, so that you can pitch some product to them with confidence. The similar problem is with YouTube. Either music or video, you go to watch YouTube, either for music or video. What do? We see that people watch some song or listen to some music, but then we don't really know what else to suggest next, because the customer might be coming to you for the first time and you may not really know what they will like. So there are too many options to show you, but to a particular listener. The same thing with Netflix, and the same thing if you go to any other bookstore where they sell online books. So these are what are called as the problems of scale. There are thousands or millions of customers, and there are thousands of products. And from one customer buying 3 products or 4 products, you cannot really have a rule-based approach to say if a customer buys these 3, suggest the 4th one. It is very difficult to frame rules for all these kinds of scenarios. So this is where the data or the data science would come into play, or the recommendation systems would come into play. Now, when we go to look at problems of scale, meaning millions, thousands of customers and thousands of products, how do we make sense out of all this? There are some things that we need to understand. So what are those things that we need to understand? Let us see. So we are calling them data-driven approaches. And what is the data that we have? Let us look at the different types of data that we may have. So basically, we have 2 types of data. One is called as an explicit feedback, and the other one is called as implicit feedback. Explicit feedback is popular in the context of movie ratings. So if you watch a movie and you go and rate the movie, either on IMDb or Amazon. So if you know, Amazon and IMDb are basically same. IMDb is owned by Amazon. Let us say you go to Amazon Prime to watch a video and then go back and rate that particular video on IMDb. From that, they get an estimate of your taste profile or your preferences, because people who has given similar ratings to that movie are known to IMDb, so they can see that you are similar to somebody else, and they can start showing you movies which are relevant to you based on the rating that you have given to a particular movie. So in this example, we see 4 people: Alice, Bob, Charlotte, and Dexter, ABCD, who rate 4 movies, and based on ratings given to these 4 movies, we can tell whether Alice would like Titanic or not. Alice has given a high rating to Star Wars and a low rating to Seven. then somebody else who has given rating to Star Wars and rating to 7 are looked up, and then from there you figure out. We will see how to do that. But this is a case where there is an explicit feedback from the customer, meaning the customer has explicitly said on a scale of 1 to 5, this is the rating I give to the movie. So this is where the customer's taste or the preference explicitly, meaning spelled out correctly. The other case is implicit feedback, where they go and buy something online, but they don't really tell you whether they like it or not. So think of it like Amazon. You go and buy 4 things: a computer mouse, a perfume, a watch, and a flower vase. So customers have bought this. We don't really know whether they bought it for gifting it to somebody or whether they bought it for using. If they have bought it for using it for themselves, then we can make some reasonable recommendations. But they have bought it, keep buying perfumes repeatedly, then you know that they use perfumes. Then you can suggest a higher priced perfume to them. But if they have bought it only once, what do we do? So these are called as implicit feedback, where the customer's preference or customer's objectives are not clearly known. You don't really know what the customer is thinking of this particular product. You only know that they have bought the product or purchased the product from you. So these are the 2 kinds of customer feedbacks that you will get, which is either explicit in the movie ratings or music ratings, or implicit like purchases, online purchases or something like that. Now, the other kind of data is what do you know about the product and what do you know about the customer. So there are various aspects to the products. These items are different. They can be songs, videos, books, or toys, or electronic items, or whatever. And each one of them will have a feature, lot of features in them. Very simple example is a mobile phone. So if you think of a smartphone today, the smartphone is not equivalent to all of us or most of us. So if you think of people who buy smartphones, so people like say you and me, teachers and faculty, will be using them for communicating, talking to their colleagues, or talking to them on their video meetings and all. But if you think of smartphone user who is a kid or a teenager, for them it will be gaming. They would want battery life. We would want something else. If you think of somebody who will travel and take photographs, for them a smartphone would be something which will capture very good photographs. So they would be looking after phones which will have say 48 megapixel cameras. Whereas we may not really be bothered. We will be bothered only about battery life and good communication and maybe dual SIM. If one SIM goes out, we will talk to the other SIM. That is what would be a good ideal smartphone for us. But for somebody else, it is different. So the same product will have a lot of features which will appeal to different classes of people. So the same smartphone recommendation, you cannot recommend the same phone to different customers. You need to know what is the feature in the phone, what is the profile of that customer to make any good recommendation. And then there are combinations of features, especially when you think of it in terms of movies or videos or songs. It is about the lyricist, it is also about the music director, and it is also about the hero or the heroine. So you may like some artist, you may want to listen to their music. And if you like a pair of artists, say someone singing, S.P. Balasubramanian singing and Ilayaraja's music, you will only listen to their combinations and songs of their combinations and not to maybe other people. So if you think of things like music and video, there are even combinations of features. It is not simply the music director or the singer, but both of them put together. Now, coming to the customer aspects. So what is it about the customer that will make it difficult for me to simply identify what the customer would want? So the customers will have products which they purchase once versus repeat orders. So repeat orders are what they will repeatedly buy. You can easily assume that it is for their house. You can think of it that the customer want to buy it for their house. So they buy repeatedly every month or every week or something like that. And then music and video, do they watch or hear continuously or do they skip? So if one simple example is people watching videos or songs while they're traveling. It is not common today because all of us are locked down. But in the days before, when people were traveling freely, they would watch a video while they're traveling, say from home to college or going back home from after the office or something of that sort. They'll be listening to music or they'll be watching a movie. So you should know what kind of movies or what is their usage pattern so that you can give a suitable recommendation to them. Similarly, books, whether they read through or whether they regularly read or whether they skip, these kinds of things all are known if you are using something like a Kindle, e-book reader. If you are reading on an e-book reader, the company or the seller will very well know how frequently or how regularly are you reading. Are you reading 5 pages every day, or you come once in a while and read 20 pages and go? These kinds of things they will know. Then whether you have explicitly given a rating or like or whether you have said nothing. So Amazon will also ask you if you have bought some product on Amazon. Amazon will ask you, can you give a rating? Whereas you may always not give a rating. You may simply skip the rating process. Now, so when we have this data, the data about the products with all their features, data about the customers with all their behavioral patterns, how do we go to build a recommendation system? That is what we will see now. So there are two views to it. One is the user view. If you think of a user, let me find out similar users who are like him or her and suggest what they are buying to this particular user. This kind of understanding is called user view. And we have what is called as a collaborative filtering approach when we do recommendation systems. There are two classes, memory based and model based. We will look at them in detail now. Then there is another we call item view. If people listen to this song, what are the other songs they are most likely to listen to? Like the example we saw earlier, like if let us say you like Balasubramaniam's SV Balasubramaniam singing and Ilayaraja's music, so you listen to one song, then I know that these other items are similar to this particular item. They have the same singer and the same musician. So let me recommend these items to this particular customer so that he or she may like it. This is called as the item view. Then there are some things called as hybrid methods, methods that will combine both the user view as well as the item view. And there are some other approaches. We will see each one of them in detail now. So the other approaches are risk aware, location based on multi criteria. We will see as we go to the slides. So any questions so far, or I hope it is clear to all of you. Any questions so far? Okay, I'll move on to the next slide then. Yes, sir. Okay. Okay, so moving on, the first one is collaborative filtering, which is user view, where we look at similar users. Now think of this example. There is a person who is buying a particular kind of pizza and who is eating a kind of salad. The person sitting on the cycle has bought a pizza and a salad, and you want to recommend something to him. Now what do? You go and look up in the database to find out other people who have bought the same pizza and the same salad. So there is another customer B who also bought the pizza and the salad, and he also has bought an energy drink. So most likely these refer to the customer profile. This guy is an athlete. In reality, you may not really know who that guy is, but in reality, this guy may be an athlete who eats healthy food. So he is eating pizza with say mushrooms and eating salads. He's also drinking this energy drink. And another person A buys these two, then you are very likely that you can recommend the energy drink to the person. Even though you don't really know each of them in person, you don't know each of them or by their name, you only know them by the products that they buy. So for a user with given products, the person on the cycle, he has bought these two products. That is what you know. Find other users who bought these products. So I'm finding out some person B who has also bought these two products, and then see what B has bought. B has also bought an energy drink which A did not buy yet. And then what do? We suggest this energy drink to A. Now think of just one thing that may happen is B would have bought lot of products. Then what do? Do we simply suggest all the products to A? No. We look at 10 more people like B. We look at 10 other people who are also like B or who are also like A, who bought pizza and salad, and see what they bought and pick up the most common ones in the group and then suggest. So if all of them seems to have bought the energy drink, you will suggest the energy drink to A. So this is how collaborative filter works in the simplest context. This is how you go with collaborative filtering. Now, how do I do the collaborative filtering? So in the collaborative filtering, there are two approaches. One is a memory based and the other is a model based. The first one is memory based, which is what we will see now. So in the memory based collaborative filtering approach, all that you know of people is you give them some coordinates based on what they buy. Let us say one person buys 10 items of energy drink and 20 items of pizza over time, and somebody bought say 5 items of energy drink but 15 items of pizza over time. You know what is their similarity, how close they are in a product space. So it doesn't really mean pizza and energy drink, but you can give them some coordinates. X times of item 1, Y times of item 2, Z times of item 3. It can be an n-dimensional space if they have n items. So for every person, they have a coordinates. They have a set of coordinates, basically a group of XYZ values based on how frequently or how many times they have purchased these products. Now, once you know two customers with two different profiles, X1, Y1, Z1 is number of times a person bought a drink and a pizza and a salad, and x2, y2, z2 is number of times user 2 purchased the drink and the pizza and the salad. Then we can go on to do some metrics. It is like coordinate geometry now. The moment you have these numbers or tuples as you may call them, we can go to our coordinate geometry kind of an approach to see how correlated are they. If they are buying x1, y1, z1, x2, y2, z2, how similar are they? That is one thing you can do. The other thing you can do is how far are they from each other, which is a simple distance rule. So people who are very close or people who have similar preferences will be close to each other. So one example is, let us say the person goes on a cycling trip. After every trip, he will eat the pizza and buy the drink. Then he will have equal number of purchases for pizza as well as the drink. So for him, x1 and y1 will be equal. So another similar person will have similar x1s and y1s because he is also going on cycling and he will eat the pizza and have the drink after the pizza. They are also likely to have the same number of pizzas and drinks. So they will be very close to each other on the graph, and you know that A and B are close to each other by the Euclidean distance. Another metric that people use is cosine similarity. What is the angle between the two vectors? Given that vector will map from origin to this particular person. So one vector is to the person 1 or user 1, other vector is to user 2. What is the angle between the two vectors? Lower the angle, higher their similarity. This is another approach. So these are the three ways of measuring the similarity between users, where users are quantified by the behavior. The behavior is basically a set of coordinates for the number of times they have brought each of these items. If you have n items, it will be an n-dimensional space, and they will have n, each user will have n numbers. Each number will refer to number of times a particular item is purchased or bought. And then once you are able to map all the users onto the space, you can find out who are similar to each other or close to each other. Then, so that is how it would work. And then there are two variants to the problem. The two variants to the problem are user collaborative and item collaborative. So what are these two? We will see. So what is user collaborative filter? There are lot of items and few users. Let us say you are referring to people who buy some things in a local store. You will have lesser number of users but more number of items. So basically each user will have bought more items and the rate of few items, but each item will have very few ratings. Say there are 100 people buying 10,000 products, and each person may buy 3 or 4 or 5 products. So each product will have fewer users, but each user will have more products. That way you have a better view looking at the user interaction rather than the item interaction. So ratings per user are more than ratings per item. So each person has bought 3 to 5 products. So I know more about him rather than looking at the item where most items have only one purchaser. That is a simplification, simple statement. So what do? We normalize the ratings for each user. Suppose users go and rate these items, then we will normalize the rating for each user. By normalize, we mean there are some people who usually tend to give higher ratings. There are some people who usually give lower ratings. So somebody rates movies 1, 2, 3, 1, 2, 3, 1, 2, 3 only, you know that this guy will give lower ratings. Somebody rates 3, 4, 5, 3, 4, 5, you know that he or she is a kind person who will give bigger ratings or higher ratings to each of the movies. So we have to normalize. So we do a mean of the ratings and then normalize so that we can understand the true variation among products. And once we normalize ratings for each user, we go and find out users who have similar ratings on other products, or users who have given similar ratings for these products. And so for a user, we will predict the unrated items. So one example is this. Let us say the two users you see on the top have purchased grapes, strawberry, watermelon and oranges and given some ratings. And then the person below also has bought watermelon and strawberry and given some ratings. And the person in between has given a rating only to strawberry. What do? We go and look at the rating that the person in the middle has given to the strawberry, find who else has given a similar rating, and then try to suggest items that by that person to this person. Let us say the user 2, let us call them user 1, 2, 3. User 2 gives a high rating to strawberry. User 3 gives a low rating and user 1 gives a high rating to strawberry. You know that user 1 is more similar than user 3 to user 2. So whatever user 1 has bought, we will suggest them to user 2. That is how user collaborative filtering is done. So what do? Once we identify all the ratings or we guess the ratings, we predict what are the items that user 2 is most likely to buy, given that user 2 is similar to user 1 or customer 1. So if you know 10 items that customer 1 has purchased, I will take these 10 items and suggest the top n. By n we mean it can be 3 or 5. Suppose you want to show top 3, from the 10 we will pick up top 3 which are most likely to be purchased by user 2, based on their understanding that user 2 is similar to user 1. This works very well. This understanding is very fine, but it has a higher computational cost because there are a lot of items and few users. You have to evaluate the ratings of each of those items for each of the users. So it will take long time to run, and it is very good, or it is suitable for offline recommendations. What do we mean by offline recommendations? You go to Big Bazaar or more or something, buy something and come back. Next week you get a message telling these are the items which are on sale for you. So from your last purchase to now there is some time. I need not tell you immediately. I need not recommend something to you immediately. I know that you will come back after a week or 2 weeks, and before you come I can send you a suggestion or a recommendation. So when there is a time between the recommendation, when there is a time between the customer purchase and the recommendation to be made, these are called as offline recommendations. You can take 1 or 2 days to go back to the customer, and user collaborative filtering works very well when you have offline recommendations. So retail store, somebody made a purchase this week, I can go back, compute, take time, but find similar users, and then find out most relevant products, and then send a mail to you or send a message to you after 3 days telling that, okay, we have these items on offer for you, 5% off on oil or 10% off on atta. That kind of thing they can do next week. There is time. Now, the other problem is in terms of when there is no time. Think of it like Amazon Prime or Netflix or YouTube. You keep watching the movie or the video or the song. They should recommend something by the time the song ends. They cannot take 1 week to come back to you telling, okay, you watched this song last week. Do you want to watch this song now? Usually, people watch or people spend time online in sprints. So they spend some time on YouTube when they get time. They may not really go back to it regularly at the same time tomorrow or day after. So in such cases, you don't have much time to make a recommendation. You have to say something on the fly. So when you have to make a recommendation on the fly, that is when item collaborative filtering is used. How does it work? In the item collaborative filtering, we will have few items but more users. There are 1,000 songs by a particular in a particular genre, but there are millions or thousands of users or 100 lakhs of users who will listen to this song. So a particular user comes and starts listening to the song. What is the next song I can suggest to this user? It is very difficult for us to find out similar users, but it is easy for us to find out similar items. Now, why is it by item I mean song? How is it easy, or why is it easy to find out similar items? There are more ratings per item than ratings per user. A user may rate 10 songs, but each song will have hundreds or thousands of likes or dislikes. So each item has more ratings than each user giving some ratings. So users will give 5 or 10 ratings at most, but each item may have hundreds or thousands of ratings. So we know better about the item than the user. So when we know ratings given to a particular item or when we know ratings given to a particular item, we go back and find out items that have similar ratings. What are other items which were rated similarly, and then suggest those items. So recommend new items to a user based on the similarity. Here the computational cost is lower because items have dense ratings and you can compute it once in a while. You need not really change your item ratings every day. So let us say there are a particular set of songs that people listen very regularly. That particular set of songs will not become useless tomorrow. The people's preferences will not change so quickly that by overnight it will become redundant tomorrow. You know that these songs are similar category or similar genre. People usually listen to them together. So you are comfortable making the same recommendation even tomorrow. There is no need to worry about recomputing it every day. Also, you can handle varying user profiles. If different people come to you, it can also handle user profiles because it is not really worried about the user, but it is focusing on the item. So different people come, you don't have a problem. You can suggest the same item with good confidence, and this is useful for on-the-fly recommendations because you have pre-computed it already. You are not computing it when the user starts watching the song, but you already have an estimate of what are the songs which are close to each other, or what are the songs which go together with the majority of users. So here the recommendations are pre-computed, no need to worry. and then you can show them on the fly. You start watching one song, they will have a list of 10 recommendations ready for you because it is pre-computed. So this is the second variant of user-user or collaborative filtering approach, where you look at the user-user similarity or item-item similarity. So what are the algorithms that are used for these kinds of collaborative filtering approaches? Slope one is one algorithm. Slope one is a simple algorithm, uh, and this is a simple algorithm which will try to keep the computational time small. So you can use lot of there are many algorithms present. Most of them will take a lot of time to compute. So slope one is a simple approach. When you have lot of users and lot of items, what do we do? Now look at it as an example. There are two users, user A and user B. There are two items, item I and item J. User A has given ratings for two items. Item I, item J, he has given two ratings saying 1 and 1.5. User B, what is the rating for user B for item J? Why do we need to know this rating? Only when we know the rating can we suggest the items which user B is likely to watch or likely to buy. So basically recommendation system is about predicting an unknown rating. What would the rating be for item J if user B gives a rating? Or what would user B's rating for item J be? This is what we are trying to guess or estimate or calculate. If we calculate this and if the rating is very low, we know that user B will not like or may not like item J. So I will forget about item J. But if the rating is higher, then user B is likely to watch or buy item J. So let me recommend item J to user B. That is what we are trying to do. Now, so slope one algorithm works like this. So user A has given ratings for item I and item J 1 and 1.5. User B has given rating 2 to item I. What would user B's rating for item JB? We estimate. So between item I and item J, there is a difference of 0.5 for user A. So I am just simply estimating that the same difference would hold for user B also. For in a normal scenario, user A, user B are kind of similar people. So if user A rated item J 0.5 times higher, 0.5 higher than item I, user B also would give a similar rating. This is all slope one will do. It will say 2 plus 1.5 minus 1 or 2.5. User B is likely to rate item J at 2.5. So once we know this rating, we can find out whether user B is likely to buy item J or not. And from there, we can go on to show the recommendation. The calculation is simple. It will only look at one other user. For every user B, it will only look at one other user. It will reduce latency. There is not much of time required to compute this, and also not much of memory required to compute this. So you can get a quick answer or answer on the fly. So slope one is a popular algorithm that people use. And why do they use it? They don't use it just because it is simple or easy to calculate or it is low memory. It will do as good as computationally complex algorithms. What do we mean by as good as? When I show a recommendation, how likely is the user to take up that recommendation, either buy the product or watch the song? That is a metric. We will come to the metric sometime soon. But if the algorithm is useless, it is saying something, but the no users are really looking at it, that is a bad algorithm, right? So slope one is an algorithm which will do as good as computationally complex algorithms in terms of user adoption, user taking up the buying the product or watching the movie. Now, what are the metrics for the algorithms? We will come to there shortly. Then we will go to the other class of collaborative filter where we build a model. There is something called as a model-based collaborative filtering. So model-based collaborative filtering is used in scenarios where the products themselves have lot of features. The products are complex. It is books, but all the books are not same. So coding language books, historical novel, historical non-fiction, and fictional novels. Although all of them are books, they are not the same. So you cannot really recommend a fiction book to somebody who is buying coding books. So they have their own differences. So when you have lot of users and lot of products which have some nuance or some set of features which are not easy to decipher, we go to what is called as model-based filtering. So model-based filtering works like this. In the simplest mathematical context or mathematical sense, model-based filtering is matrix factorization. There is a matrix X that I know, which has, say, n rows and m columns. N are the users and m are the products. So there are n rows and m columns, and the matrix is a rating matrix. So each cell is the rating for this particular item by this particular user. So user 1, item 1 is 4, user 1, item 4, item 5 is 5, and user 6 and item 3 is 2. So this is a rating item, rating matrix. So what do we have? We have n users, m products, and ratings, n cross m matrix. And in simple mathematical terms, model-based collaborative filtering is matrix factorization. Can I represent the matrix X as a product of two matrices U and V? U is called as the user matrix and V is called as the item matrix. So I want to break down this matrix into two matrices A, U and V such that U into V will give me X. So if X has dimensions n cross m, U should have n cross k and V should have k cross m. The k must be common, right? So k columns in U and k rows in V. So this is how we do matrix factorization. Now what is k? Why do we bring in k, or what is k? So k is basically what are called as latent factors. So hidden features about the product or hidden features about the user. So in the user matrix, the k latent factors will refer to user attributes. In the item matrix, the rows will refer to the latent factors of that particular item. So basically, this is matrix factorization, very simply. Now what do we do? You are saying matrix factorization, fine, but what do we do with the matrix factorization? Think of an example like this. There are 4 users A, B, C, D. There are 4 items W, X, Y, Z, and these are the ratings given by users for the particular items. So there is a user A who has rated X as 4.5 and Y as 2. User B has rated W as 4 and Y as 3.5 and so on. Now if you factorize this matrix, you get some number like this, which is user matrix for A and item matrix for B. Now what do we do, or what is the use of this matrix? If you break down this user item matrix into two matrices like this, what we can do is we can find out similar users. So look at rows A and D, they have similar latent features. There are 2 latent features for each of them, and you realize that basically that A and D are similar in the row space. A's latent features are same as D's latent features. Similarly, you can look at item similarities. What items are similar to each other? If you look at item similarity, X and Y seem to be similar, 1.2 and 0.6, 0.8 and 0.4. They seem to have a relation. So these kinds of things we will understand. We will be able to identify similar users or similar items. So the user matrix will describe user features responsible for a given rating. What are the features of the user which led to this rating for X? That is what the user matrix will tell you. Item matrix will describe item attributes that lead to a given rating. These are the attributes for this particular item which led to a particular rating by user A. So there are various factorization methods. How do I break matrix X into U and V? This is a problem that is known even in the engineering world. Whenever you go to solve other problems, this A into X is equal to B problem is known. So how do we solve? There are different methods to solve. And how many latent factors do I consider? What is the size of K? K is 10 or K is 100. That is a hyperparameter, meaning you can choose a suitable value that will give you a very good answer. Very, very large K. If you have 1000 parameters, you may get a overfitted model. You have 1 or 2 latent factors, you may get a underfitted or a very bad model. So you choose a suitable K such that the recommendations are relevant to the users. So this is about the model-based collaborative filtering approach. The only call out here is that the latent factors themselves. What are these numbers? What is 1.2 and 0.8 for A? Or what is 1.5 and 1 for C? These are not interpretable. You cannot simply say this is A's likelihood of suspense movies and this is C's interest in action movies. You cannot say 1.5 is C's rating for action suspense and 1 is C's rating for action. There is no separability like that, and you cannot really interpret the latent factors. That is the only small handicap of this approach. But given this approach, you are very, very well equipped to find out similar users and similar items. Now, what is one algorithm to do this problem or to solve this problem? There are different algorithms: singular value decomposition, SVD, non-negative matrix factorization, which is another approach, NMF. These are all approaches to do the matrix factorization. X is equal to U into V to solve that problem. Why do we want non-negative numbers? Just to understand, there will be no negative ratings here. Nobody will give a negative rating. Rating will at most be 0. and at least be 0 and at most be 5. So if the ratings are positive numbers, we cannot really have negative numbers for A or B. So the latent factors themselves have to be positive, at most close to 0. So which is why we go to what is called as non-negative matrix factorization or SVD. Then there is another approach or third algorithm which is called as the alternating least squares. So ALS algorithm is we'll do the matrix factorization. How does it do? It will assign random values to user and item matrices. It will start with the user and item matrix. It will start with a matrix like this and a matrix like this. It will assign very, very small but random numbers to the latent factors that you are considering, and then go on to do what? It will assign random values. It will predict the rating and estimate the error. So given the latent features for users and given the latent features for the items, what are the ratings that will come for these user cross items? It will predict and then estimate the error. And based on the error, it will update the latent factors. It will hold the item matrix study and update the user matrix. It will alternate and go and hold the user matrix study and update the item matrix. So very simply put, what does it do? It starts with k latent factors for users. If I may go back to the last slide, it will start with k random numbers here and k random numbers here and predict the ratings. Let us say it has given 2 random numbers for x and 2 random numbers for y. It will multiply these two, a and x, and see what is the rating. If the rating is 3, it will hold these numbers steady and update these numbers and then recalculate the rating. The rating will be 4, let us say. It will hold these numbers steady and then update these numbers. So iteratively you keep updating the numbers for the user and for the item until you get a good answer for the rating that is given by the user for that particular item. You do the same thing on all the items, you get your answer, which is called as the ALS method. So this method is similar to linear regression. You try to estimate how close you are to the answer. If you are not close, you adjust the coefficient. That is how it will work. And this also has a faster convergence compared to other typical methods. This method is very, very fast in doing the matrix factorization to break the user item rating matrix into user matrix and item matrix. So this is about user collaborative filtering. So far we have looked at approaches which will try to find out similar users or similar products using a approach where you know only the purchase behavior. Now any questions so far? I'll maybe wait for a while. I'll drink some water. If you have any questions, please feel free to ask.
Participants, if you have any doubt, you please ask.
So I hope it is making sense to most of you, and it is not simply.
Yes, sir. Yes, sir. It is going well.
Yeah. Thank you. So then we will move to the other part where the other part is
okay, sir.
Yeah. Thank you. So we know we'll go to the.
Sir, in the meanwhile, at the 4:30 we can give a 15 minutes break, sir, so that we will.
Yeah, this it will get over by 4:30, sir. No problem.
Okay, sir.
So the other part is what is called as content-based filtering. What is content-based filtering? We know very well about movies. They have some genres, they have some artists, they have some plots and all. We know about songs or books. Books have a genre. There are mystery books, science fiction, non-fiction, and so on. Or we know about music, classical music, pop music, jazz, all kinds of things. So in scenarios where you know something about the product that is being sold or that is for the user to consume, either to listen or to see. In case of where you know more about the products, we can bring in the product features to make sensible recommendations. That is what is about content-based filtering. So what is content-based filtering? We know these are the particular attributes or properties of a particular item. Item is a song or a movie or a book. So what do? We have vectors to describe the item features. Just like we saw in the collaborative filtering where item had features. In this case, we can have vectors to describe the item features, which we arrive at manually or which are known from from what people write or from the genre and all. So we have vectors that will describe item features. Then we do clustering or we do Euclidean distance to identify nearby items. So each song or each book has a vector or a set of features which will describe them. And if I want to recommend similar books or similar songs, we do clustering or Euclidean approaches to find out what other songs are similar to this song or what other items are similar to this item. And then these features can be explicit, meaning explicitly mentioned. This is a suspense movie, so let me bring up other suspense movies. or this is a science fiction book. Let me bring up other science fiction books. That is how the features can be explicit, or they can be implicitly inferred. If you don't know explicitly, you can go and infer. So if it is a novel, you can go and look at the text of the novel and try to identify what the novel is about and see whether this is a science fiction or a non-fiction book. So if you know, you may be familiar with the natural language processing, where you are able to read through the documents and understand what is there in the documents, who are the characters in the documents, in the novel, and what is the theme of the novel. So that and all we can do. So you can either implicitly infer by reading the documents through NLP, or the speeches can be explicitly mentioned, saying this is the genre of the movie or the book. And then neural networks can help us to learn embeddings. Once you have a text document, you go and parse the text. You can use neural networks to learn embeddings from the text and then recommend similar items. Suppose you read Harry Potter book 1, then we are very sure that you will read Harry Potter book 2, book 3, book 4, and so on. So this is very useful. The content-based filtering approach is very useful in the context of movies, music, and books, where you can identify what are the features of the products or the items being sold. Based on those, you can try to group them and say these are the similar items. And then, what do we do if I'm selling books on Amazon, or what do I do if I'm showing videos on YouTube? So to make the best of both worlds, one is the content-based world where you know about the item, song, book, or movie, and the user-based world where I know there are a lot of users and I can find out similar users. There are what are called as hybrid approaches. So hybrid approaches are basically which will combine both the collaborative filtering recommendation and the content-based filtering recommendation. Both of them are combined to give a hybrid recommendation. So somebody might like suspense movies and they may specifically like, say, James Bond movies. So the content-based will say suspense, and the hybrid, the collaborative may say this guy is only watching James Bond movies. So you can suggest James Bond movies and not say Jackie Chan or Jet Li movies, for example. Just an example to differentiate. So hybrid recommendation will bring in the best of both worlds. They will learn about the user from collaborative filtering. The user has watched 5 or 10 movies. I know similar users who have watched these movies. And I know the item attributes. This guy has watched these movies, and I know the attributes of these items. They are suspense movies. And then combining these two by weighting them or cascading or switching, they'll combine the recommendations from the collaborative as well as the content based and come to an answer. So these are called as hybrid approaches. And what do we use if we want to do a hybrid approach? So there is an open source tool called Light FM. Light FM is free. It is a hybrid recommender. You can go to this place lyst.com and download. It will take in the user and item matrix and then give out recommendations. And while doing that, it will make use of both user attributes and item attributes. It will break down the user item rating matrix into user matrix and item matrix, get the latent features, and from there it is able to make good recommendations. Now, it is able to overcome the problem of cold start. What is cold start? If a user comes to the website first and only watches one movie or listens to only one song, I don't know anything else about the user. That is called the cold start problem. I don't know much about the user to make a sensible recommendation. If he has watched 5 movies, I will know very well what is his taste. Or if she has listened to 10 songs, I will know what is her musical taste. But if he or she has watched only one movie, I don't know anything. That is called the problem of cold start. Collaborative filtering approaches suffer from that problem. They don't do very well when the user has only one item. But the item-based thing will help you in that case. If the user has come and listened to one, say, classical music, Carnatic classical music song, you know, because the item is Carnatic classical music, you know that you can suggest similar items which belong to Carnatic classical music, just for an example. And then, the content-based filtering approaches have another problem of diversity. So Light FM will solve that problem also. It will provide diversity. Now, what is diversity? Diversity is this problem. If I purely do content-based filtering, I don't look at the user profile. I only do content-based filtering. And let us say the user has listened to one song of SP Balasubramaniam, and we only stick to content-based. The user will only recommend his songs. It will not recommend anything else. There is no diversity. All the songs that are recommended will belong to, say, sung by SPB. So where is the diversity there? It is not there. That is the problem with content-based approaches. So collaborative will provide diversity. Content-based will provide the cold start, will solve the cold start problem. So Light FM will solve both the problems. and it will do well when users have only one item that they have purchased or seen or used. There are other recommendation systems also. Some of them are called as the multi-criteria recommendation. They evaluate multiple criteria for suggesting an item beside the preference. So one example of multi-criteria systems are like this. Let us say you go to a supermarket and regularly buy oil and rice. And from the model, you are able to estimate that this particular customer will buy rice, a bag of, say, 25 kg bag of rice every month, as an example. And then after you do that, you bought a bag of rice on 1st of November, and they are going to send you a recommendation. The supermarket wants to send you a recommendation by mail or by message on 7th of November, 1 week after your purchase. So one criteria there is rice will come up as a popular item, but another criteria there is that you bought rice only last week and you usually buy after every month. So there is no point in recommending rice to you. So that criteria of the frequency of purchase is taken into account, and then rice is eliminated from a recommendation. They will recommend something else which you did not buy last week. So this is an example of what are called as multi-criteria recommendation systems. Not just looking at popular item, but also looking at other criteria which is relevant to the popular items. The other class is location-based systems, which will refer or which will give you recommendations when you go to nearby places. So you go to some place and turn on your Google Maps, it will tell you there is a good hotel nearby you want to go and see, or there is a landmark, do you want to visit the landmark. These are called as location-aware systems. The last one is called as risk-aware systems, which will know what time should I send a recommendation. If they know by some means, if they know that you are an office-going professional who will be in office from 9 to 5, they would not send you a recommendation at 10:30 or 11:30 in the morning. They will only send it after office hours, because during a meeting, if you get a recommendation, you are more likely to be irritated rather than be pleasantly surprised. So you will not have time to really consider when you are in a meeting if a recommendation comes. So these are called as risk-aware systems, which will identify. If they have an app, it is very easy for them to identify your active time. So let us think of the Amazon context. If you browse Amazon shopping app in your phone for regularly, they have a very good idea of what time does this customer browse the app. Based on that, they will send you recommendations during that time. And if you are an office-going professional and you don't use the app between 9 to 5, they know very well that between 9 to 5, this person is in work. And I should not send any recommendation that will ping the phone at 9:30 or 10:30 in the morning. These are called as risk-aware systems. And then we'll move on to a few advanced topics. These are just for reference. You are free to read up and go, but we will talk about them briefly. The first one is what is called as a neural collaborative filter. So the neural collaborative filter is basically where we use neural networks to identify the latent features for items and users. In the previous example that we saw of collaborative filtering, what did we see? We saw that the items and the users form a matrix, and we decompose the matrix into two by doing simple ALS or something of that sort to identify the latent features. But then we can also use neural networks which will solve the problem. How do we use the neural network? From the item, the neural networks are used to construct what are called as the latent vectors. This is much like embeddings. If you know word embeddings in natural language processing, the neural network will construct embeddings for a given one-hot encoded word. You give a one-hot encoded string, the neural network will give an embedding, a dense embedding. So similarly, we can use embeddings to identify latent features for the users and latent features for the items, and take these latent vectors and go on to give a recommendation score. So these neural collaborative filters are very useful when the products are complex. There are a lot of complexities in the product features and also complexities in the user behavior. When these kinds of things are there, you are well off using neural collaborative filtering approaches. And then deep factorization machine is another approach where you just don't send in the one hot encoded vector, but you send in the item features, input features. So if the product has 20 features, you send in the 20 features of the products and then try to identify a recommendation. So this is another approach which is called as a deep factorization machine. Not very commonly used, but very, very advanced problems and all, you may consider using either of these, neural collaborative filter or the deep factorization machine. Then coming to the evaluation of the recommendation system. If you remember, a few slides ago we mentioned slope one will do as good as complicated algorithms. How do we know slope one will do as good as complicated algorithms? So there are approaches or means or ways to identify or to measure the efficiency of recommendation systems. So what are they? We will see. The first one is what is called as a point-wise loss, which is an RMSE error for the ratings on the test and the holdout data. If you are thinking of explicit ratings, users have rated movies and I am building a recommendation system. What will I do? I will hold out a few known ratings for some user cross items. I will hold out some numbers in the array and try to predict those numbers. So it is like predicting any continuous number. I predict number 4, but the answer is 5. I know an RMSE error. So this is called as a point-wise loss, especially useful when you are thinking of ratings that are explicitly given. Then the other concept is pairwise loss. Pairwise loss is given by this ROC AUC curves, where if you randomly choose a positive example for a particular user, it must have a higher score than a randomly choose a negative example. By this we mean there is a user and there are two items, item 1, item 2. Item 1 the user is likely to buy, item 2 the user is not likely to buy. Item 2 is negative for the user, he will not buy it, and item 1 is positive for the user. So if you pick up these two items, item 1 must have a higher score than item 2. It cannot be the other way around. So this must hold for all the users and for all the items. So how do we do this? We do this by using our ROC curves and all. So it is like a classification problem. Then the other metric is this. You cannot really recommend 1,000 items. If you want to make your recommendations work, a simple shortcut is let me recommend all the items. I have 1,000 items on sale. I will recommend all the 1,000 items. The user will eventually buy one of them. If the user eventually buys one of them, you can say that I recommended, he bought. That way I am good, no problem. But in reality, in the real world, you don't have the luxury of recommending 1,000 or 10,000 items. Because you send messages via SMS, or because you send messages via WhatsApp, or because you send messages on email, you can only recommend 3 or 5 or at most 10 items to customers. So what do? When we build a recommendation engine? We recommend K items for the users and then see of the K items recommended, how many are accepted. So this will lead to metrics which are called as precision at K and recall at K. So what is precision at K? The fraction of known positives in the first K recommendation. If I get ratings for 20 items, I pick the top 5 based on the highest rating and show the top 5 to the user. Of the top 5, how many did the user buy? This is called precision at 5. The other one is recall at 5, which is simply what is the fraction of known positives in the test data. If the user bought 10 items and I pick up top 20, where do I hit the 10 items? If I show 5, how many is the user buying? The user is buying only 2. Then recall at 5 will be something 2 by 10. If I show 10 items and the user is buying 8, recall at 10 would be bigger number than what you saw before. So precision and recall at K are metrics which are used when you are constrained to recommend only K items to a particular user. But what happens in the real world? What we saw so far, all the metrics that we saw so far are when you are building the recommendation model. There is a data set. I build a recommendation model. I want to evaluate the model. So that is till there is what the precision and recall will help us with. But in the real world, what do we do? In the real world, what we do is what is called as an A/B testing of customer conversion or increase in purchases. So think of it in a simple again supermarket example. Think of it like this: you have 1,000 customers in the supermarket, and you build a recommendation engine for those customers. You don't send out recommendations to everybody. First, you want to see whether this recommendation is useful or not. So what do? In the 1,000 customers, you break them into 2 groups: test group and control group. For 500 people, you don't do anything. You send random recommendations that you are doing before. Whatever you are doing before, you keep doing for the 500 people in terms of reaching out to them. For the other 500 people, you send recommendations that come from your recommendation engine. And then what do you see? What you measure is you measure lift, whether in the test group to whom I send recommendations via the recommendation engine, are there higher purchases? Are there higher visits to the store? Or is there an increase in the average item value? These are the numbers that you will measure. And if you see any positive in any of these metrics, then your recommendation engine is working well. So the customer may not really come to your store for buying that particular item only, but he may come for buying something else. So increased store visits is one metric. Increased item value, what is the average item value you buy? That is another metric. And whether you are buying recommended products or not is a third metric. Then apart from these three, there are other metrics also which are considered, which is diversity. Items with high intra-list diversity are preferred, meaning if you know one item, you should not continue to show items which are closely related to this. Meaning, if you show cool drink, you should not keep showing cool drinks only. You should not say, if somebody bought Pepsi, you should not keep saying Coca-Cola, Sprite or Fanta or something. You should try to switch to say chips or biscuits. That diversity must be there. And there must be persistence. Sometimes you reshare recommendations because of repeated products. If customers have some health drink regularly, you are better off showing it once in a while. So there must be persistence. And the privacy and demographic information. Most of the time you don't really know very much about your customer because of privacy. And you also don't know the customer demographics. Meaning, if somebody buys Horlicks, you don't really know whether they bought it for a middle-aged person or whether it is for a kid. And then the recommendation engine must also be robust to fraudulent ratings. If you are thinking of ratings on IMDb or YouTube, it must be resistant or robust to that ratings as well. It should not be it should not get carried away by high or low ratings. And then sometimes they should show surprising recommendations, which the customer may usually like. There is no way to really say how do I show surprising recommendations, but you are well off showing it. And what are the challenges when you want to build any recommendation engine? What are the challenges that you face? Data sparsity. By data sparsity, we mean each user will only buy few items, and each item will only have few users. Not everybody will buy every item. Not everybody will rate every item. So in the entire catalog, if you go back to our first slide, 150 million customers and 12 million items, each cell in the user item matrix will not be populated. It will be a very, very sparse matrix. And then scalability. As the number of users grow, number of items grow, the computational time will increase, either for ALS or for any approach for that matter. The computational time will increase. At 1,000 items, 10,000 users, if your computational time is say 2 hours, at 20,000 users and 2,000 products, it will become even bigger. It won't simply be double, it will be like 2 days or so. So computational time will increase. And then there are synonyms. People may refer to aviator and wayfarer. Aviator and wayfarer are referring to the Ray-Ban glasses only. So the text-based recommendations must need to know these kinds of nuances. They are referring to glasses and not referring to something else. And then there is a problem of grey sheep. Some people will always rate consistently lower. Some people will always rate consistently higher. Or some people will always rate some particular class of products very badly by some particular company. These are called grey sheep. Because of some reason, they give a low rating. You should have a means or way to normalize the ratings. Then shilling attacks are where users will rate their own items well and give low ratings to competitors. If you think of Amazon where sellers rate items, sellers who are selling a particular product will give very high rating to their own product and then give low rating to the competitor product. These kinds of things are possible. These are called as shilling attacks. And then there is always the problem of long tail, where there are a lot of items which are bought rarely. There is an item which is bought only by 10 people when you have 1,000 customers. I don't really know whom should I recommend the item to. These kinds of problems are there. Infrequent items, they will not be recommended because they don't have sufficient data. You always tend to recommend items which are more popular with customers or more popular with people, which is a natural thing which cannot be avoided. In the business world, what are the considerations? If you want to deploy this to a particular business, what are the considerations? There are considerations about margin and revenue. So suppose you build a recommendation engine for a particular store or for a particular, say, supermarket, and then you deploy. And what do you see? The customer is buying some item which is 100 rupees per bottle, say Horlicks. And you know that they are likely to buy some other item which will cost 80 rupees per bottle. And then there is also some other item which is less preferred, which is rated as next, but that item costs 110 rupees per bottle. So even though you know that the cheaper item is strongly recommended, the supermarket may not be willing to take that because people are buying high ticket items. They are buying $100 bottles, 100 rupee bottles. I am better off moving them to 110 rupee bottles rather than moving them down to 80 rupee bottles. Why to the high price item? Because they'll have higher margins there. So you may have to recommend a less preferred but costly item compared to a cheaper but highly preferred item. This is a business consideration that will come into play. The other one is response time. Do I have the luxury of doing an offline recommendation? Can I reach out to the customer after 2 days? This is possible when you have customer info like email or phone number. But some customers for whom you don't have any email or phone number, you have to suggest them on the fly. Meaning that if you are building items for them, the computer terminal or the POS terminal must show up some recommendations for that particular item for that particular customer based on what are built. This is called on the fly. Then there is a third concept of identifying customer journey and making more informed recommendations. Meaning, if there is a supermarket and people have been coming to the supermarket for years, you know that customers also age. So somebody who may be coming 10 years before will be buying, say, college student kind of items from your supermarket. They might be buying, say, Boost or Horlicks or tennis balls or chips and items. Now that person would have come to middle age. He will be buying something else. He or she would have been married, and then you know that they might have progressed on in life. So you start recommending rice or pulses or atta or something to them. So if you fast forward it 20 more years, you will start recommending pain relief oils and Amrutanjan bombs to them. So this is the customer journey where the customer spends the time with the particular company for a long time. So these are the things that you need to take into consideration. So that brings us to the end of the talk, and thank you very much for listening to me patiently. And I hope I have made some sense to you, and I hope the presentation made sense. I will be willing to glad to take any questions. Yes, sir.
Participants, if you have any doubt, you can ask.
Or maybe I'll go to the AI links and stay there so that people can establish. Any questions, sir? It can be on recommendation systems or it can be on any other thing, no problem. So just for me to understand, most of you are faculty, right? Is that correct, sir?
Yes, sir. Yes, sir.
Okay, fine. It can be an academic question also. What language to teach and all? Because I am also, I also used to go and teach in colleges or take classes to students once in a while in a workshop. If you have any generic questions, may not be exactly related to recommendation systems. Anything else also, you are free to ask. No problem.
Participants, please.
Excuse me, sir. Good afternoon.
Good afternoon, sir.
Good evening, rather. Sir, may I interact with you?
Sure, no problem.
Sir, so nice to have your presentation. Very enriching. But it's not a doubt, sir, but it's just a kind of clarity I'm just asking. Will this big data analysis, is it applicable under a certain specified normal conditions or any abnormal conditions also? This big data analysis can be used for decision making.
Yeah, yes, sir. So that is an interesting point because I also have a lecture on December 1st. I will be talking about that there, sir. It is called anomaly detection. You see a lot of observations, and you know what is a normal. How are these things normally appearing to you? And then if something goes abnormal, you will be able to identify. So there is another class of problems that are the other class of algorithms, which are called as anomaly detection techniques, which we can use in a big data world to identify probable faults or failures. So one example is a communication network, sir. Let us say there are cell towers, and each of these cell towers is attending to some certain number of users, and the number of users who are using that particular cell tower will vary with time. But then there is some abnormality you will know from anomaly detection on the big data, because there are a lot of towers, they send a lot of info. You will be easily able to identify if there is something abnormal with a particular tower. It is applicable there. There are tools and techniques called as anomaly detection approaches to solve that problem.
Okay. Thank you so much, sir, for your explanation. Thank you so much.
Yeah, please continue. Who's asking?
Sir, any application or anything you come across, 2 or 3 recommendations we have to work together to further get the
combining recommendation approaches, right? One recommendation system, another one, right?
yes.
Yeah, so usually sir, you're continuing the question, or is it over?
Yeah, that's all question. It's over.
Yeah. So usually in the recommendation systems, what we have seen is that If you have two or three things to bring in, we bring in together, sir. Like Light FM is an example. People apply only business rules. The second stage recommendation is only based on the business rules. So the first model will have whatever you want to bring in, you bring it in the first model itself, which can be a collaborative model or which can be a hybrid model. And then the second stage is majorly driven by business rules, sir. So what I have shown here, we have actually deployed it for a retailer in the US. They have a big retail store throughout the country, and they sell some items. So for them, we have deployed it. The second stage is basically business rules, sir, most likely. So we don't filter items from one recommendation engine using another recommendation engine. That is not normal. And whatever we want to bring in, we bring in at one step only. First step only, we bring in all the features.
Thank you, sir.
Yeah.
Participants, any other questions?
Excuse me, sir.
Yes, sir.
Sir, I just want to ask one question related to if you just buy to purchase, like if you're buying the any product from let's say Amazon or Flipkart, so
Yeah.
usually for the rating, correct?
They will ask you, yes.
So
Hmm.
yeah, so is it possible to get it to know whether is that rating will be faulty or whether it is given by the customer? How do we identify that? Means is it related to recommendation system?
Okay, your question is the rating given by a user to a particular item, right? Some user will give a
Yeah,
rating to an item after they buy it.
exactly, sir. Exactly.
Ratings are normalized for users, sir. Let us say I go and rate items on Flipkart and my average ratings have been 1, 2, 3 only. They will normalize that. By normalize the mean, they will subtract it with the mean to show that these are the ratings for this item.
Sir, your voice is breaking.
I hear some background noise, sir. Somebody else talking.
Okay.
Okay. Yeah, it is okay now. Yeah. So if it is
Yeah.
a single rating for a user, there is no way to find out, sir, whether that is correct rating or a bad rating. There is no way to find out. But if you have multiple ratings given by a user, you know the user nature and you can normalize. That is what the companies do. They don't take one rating at face value.
Okay, sir. Thank you.
Yeah. There are no further questions. Maybe conclude, sir. That is.
Oh, okay, sir. We will have a break for 15 minutes. Again, the session will start at 4:45.
Okay. I
Okay, sir.
don't have anything to show, but if you want, we can do a QA for question and answer session. Okay.
Okay, sir.
Yeah, sure, sir. Okay. I'll drop off and join at 4:45. Thank you.
Okay, sir. Participants, we will have a break for 15 minutes. So at exactly 4:45, please join.
Thank you, sir.
try to pull up relevant presentation that I may have. I have something on what do you call basic EDA or deep learning.
Yeah,
Or
we can proceed, sir. We can proceed. Ask Vishnu.
okay, fine. I'll do one thing. So give me 1 minute. I hope you can see my screen, sir.
Yeah, it is visible, sir.
Okay. Yeah, just 1 minute. I'll join back. Yes, sir. You can hear me now.
Yes, sir. Yes, sir.
Okay. Yeah, I'll share my screen. I think it is visible as well. So maybe I'll talk about a few EDA techniques. I understand that we need to go until 6 o'clock. So
Okay, sir.
it already. Yeah, you would have seen some of these already, but I'll just quickly go through some topics or some things on the data side. What do we do when we do exploratory analysis? So, so machine learning is broadly two parts. One is one moment. I think it is moving slowly. Can you see the table of contents slide, sir? All of you?
The list of table of content is coming, sir. Yeah,
it's coming. Okay, it's slightly slow. So this is the brief outline. We'll talk about some things on EDA, what is data, and what are the missing. What is about missing data? Some outlier detection techniques. Our sir was asking about anomalies, right? So one simple kind of anomalies are outlier detection, and the last one is on dimensionality reduction. So these we will try to see. So this is applicable even to small data or large data. There is nothing like, is there any data scale that we need to refer to? It can apply to both small data sets and large ones as well. So if you see how, if you look at machine learning as such, it will have two major components. One is a supervised learning, and the other is unsupervised learning. Supervised learning is where we have labels for the data set to say whether it is true or false, or whether you have a number on the data or something of that sort. And unsupervised learning is where we don't have labels on the data. The data can be anything. So there is no specific label. Clustering and anomaly detection fall in this category. So we will see what both of these are. How do we use EDA in both these contexts? So regression is predicting a continuous value. Given a set of values, can I predict another continuous value? So one example is the house prices that you may have seen on Kaggle. So the house will have some bedrooms, some floor area, some area, front area, some age of the house. All these will be there. Then can we try to predict what is the price of the house? This is a typical problem that you may have seen on Kaggle. And predicting the price of the house is a regression problem where we predict a continuous number. The other class of problem is called classification, where we predict yes or no. Given a set of features, we want to predict yes or no. One example is credit card. When you apply for a credit card, whether you get a credit card or not, whether the company has to accept your application or reject your application. This is another example where the label is yes or no. Still, it is not a continuous number, but it is a yes or no label. A third class of problems in supervised learning is called reinforcement learning, where we train agents to behave or to learn something. One example is the computer game that can be taught to play chess. You can teach a computer program to play chess, and in 1996, IBM's Deep Blue defeated Gary Kasparov in the game of chess. So this is possible by means of what is called as reinforcement learning. And coming to unsupervised learning examples, one class of unsupervised learning problem is called clustering problem, where we want to group customers into different groups. So they are in a there are a set of people that come to your supermarket, or there are a group of people on Amazon online customers. You want to segment them into different groups, logical groups, to say who are youngsters, who are married people, who are old age people, and all. So this is called as a problem of clustering. And the next kind of problem is what is called as anomaly detection. This is what sir has asked in the afternoon about can we do outlier or anomaly detection. So anomaly detection is given a large set of data. Can we identify any problems or fraud with the data? So one typical example is this. Now think of say debit card swipes for all the customers in India. One simple example is people in the country have their own bank debit cards. They go and swipe these debit cards at point of sale machines to make purchases. That is common. All of us do that one way or the other. Now, what would be a typical fraud in such a case? So, a typical fraud would be that the debit card which is given by an Indian bank, meaning say let us say an example is an SBI. The debit card is issued by SBI. It has been it has been active for say the last 5 years or 10 years, and suddenly there is a transaction or suddenly there is a purchase that shows up in Europe. Okay, the same debit card, but somebody in Europe starts to there is a swipe in Europe in the middle of the night in India time. It is 3 a.m. in India. This card is being swiped somewhere in say Poland or Norway, and then that is a probable fraud because the card has always been used in the Indian in India only. It has never been used outside, and also it has this is an odd time for the people to do. This is one example of a banking fraud or an anomaly detection. Then we'll go to another class of things called as deep learning, where we have images or video. Yeah, we have images or video where we do classification of objects or detect objects or do segmentation of objects. And another class of problems are questions, where we can do a sentiment analysis of what is said, and chatbots and language translation and conversational agents. These are another class of problems which are still supervised problems in the world of machine learning. So very simple example of visual perception is this. You might have already seen it, or maybe the session will come soon. So the basic problem is simple. The first problem is classification. Given a photo, what do I have? Is it a cat or a dog? Just a moment. Yeah. Given a photo, I want to classify it to be a cat or a dog. And the second problem is the classification plus localization. Where is the cat? If there is a cat in the image, which is the second problem. Third problem is detection. If there are 4 cats and 3 dogs, or 1 dog and 3 cats, I want to locate where each of the animal is. So this is a dog with a blue rectangle. There is a duck with a green rectangle, and there are 2 cats with red rectangle. So I want to identify how many of our objects are there. I want to identify them. That is the object detection problem. And the instance segmentation problem is slightly more refined. Instead of just detecting and drawing a box around the object, we also have an outline. We'll identify this is the outline of this particular dog. So this is object detection or instance segmentation. In natural language processing, we have 4 or 5 tasks. The first task is simple, what is called as sentiment analysis. If you go back 2 slides, this is sentiment analysis, meaning people come and post comments on the website. You want to identify whether these comments are positive or negative. This is a simple NLP task called sentiment analysis. The second one is a chatbot. You go and interact. Nowadays, if you go to banks or IRCTC, you will see that there is a chatbot. So that is not a true person, but that is some computer program which can answer your queries and chat with you. Yes, sir. Somebody has a question or something?
Participants, any questions? No, sir. No, sir. You can proceed.
Yeah, sure. Then the third one is Alexa. Some of you may be using it. It is also a chatbot kind of a thing, but it is a answering agent. It will talk instead of you typing and it typing a response in text. Alexa can respond in voice. So it will understand your voice and parse the statements that you are saying, and what is behind the voice it will understand and then give an answer. So another example is also Google Voice or Siri, where they will answer your question. And the last problem, or the last one in NLP, is a robot. Sophia is a robot, which is a answering robot. Apart from question answering, it can also give emotion. It can also react. If you say something pleasant, it may react positively, and you say something negative, it may react slightly negatively. So these are the 4 tasks, common tasks that are known in NLP. There are many more tasks which are called as document summarization and entity resolution, that kind of stuff, which are done on text. Now, what is data? Data is what is key to machine learning. Any machine learning problem that you think of is possible only when there is data. Without data, there is no machine learning. So data comes in various forms, and broadly there are two categories for data. So one category is called as structured data, and the other category is called as unstructured data. So what is structured data? Structured data is what would come in tables. So there are specific columns, and each column will have a particular data type, variable of a particular data type. So if you see the housing prices example, there is a column called paved drive, and it is a yes or no. It is a categorical variable. Whereas there is something else called as wood index square feet. It is a continuous number. So structured data is organized into tables. Columns will represent the features. Rows will represent observations. Each row is one observation. It may have a dependent variable. In supervised context, there will be a dependent variable which will vary based on the features of independent variables. And the good thing is structured data is searchable by humans or algorithms. So examples of structured data are sales data, ATM card activity, visitor profile at physical store or online store and all. Unstructured data is what is not structured. We cannot put it into a table. Unstructured data also comes in different forms. One is the free flowing text that people write on company websites. You want to give comments of a particular product on Flipkart, you go and write something on the website. So this is a free flowing text, and it is not structured because you don't know what comes where, whether you are referring to the item in the first sentence or the last sentence, or at the beginning of the sentence or at the end of the sentence. These kinds of things we don't know. So this is an unstructured example of unstructured data. So unstructured data may have internal structure, but it does not have any predefined format. And you cannot organize them into tables. You cannot say all the comments are in this table and they are positive, or all the comments are in this table and they are negative. It is not easy to extract useful insights from this data, and but it is more valuable and rich than simple table data. This is more structure, more rich, or provides more information. So these are the two kinds of data that we see. Some other examples are emails that people send out, or social media posts, what people write on Facebook or Twitter or Instagram. Then images from CCTV footages, video footages and all, or documents, business documents that come in Word or PDF. So this is a simple summary of structured and unstructured data. Something is defined, or something structured data can be organized, can be searchable, is stored in relational databases, and each column has a particular data type, whereas unstructured data does not have any predefined format. It is not easy to get insights out of it, and they are typically stored in NoSQL databases and data lakes and so on. So what are the problems, common problems with any data? There will be some problems that come in when you look at any business data. So what are the typical problems? The typical problems are this: duplicate data, missing data, outliers, and then there is some dimensionality problems and there is some noise. We'll look at each of them in a while. Duplicate data is common, meaning that the same entry is repeated 3-4 times. Missing data means the data is missing and not present and you can't see. Outliers we will see as we go forward, and we'll also see about dimensionality and noise. So coming to missing data, there is a simple example of airplane armor. Maybe some of you may have seen this already, but in the simple world, in the World War II, this happened in reality. In World War II, anti-aircraft guns were developed, meaning guns which can aim at aircraft, shoot them and bring them down. So airplanes in the World War I are relatively safe. Sorry, nobody could hurt an aircraft that is flying in the air. But by the World War II time, what happens is, because of the aircraft guns, anti-aircraft guns, airplanes are getting hit and then they are falling down. So some country sends airplanes onto the enemy territory. Enemy uses anti-aircraft guns to shoot down. So because there are aircraft guns shooting airplanes, people started using armor plates. Armor plate is like a bulletproof material on the aircraft body. So you coat the aircraft body with bulletproof material so that the bullet will not penetrate into your aircraft. Now this armor was heavy, and if you add it to the aircraft, it will reduce the performance of the aircraft, because it will make the aircraft heavy, so the aircraft cannot fly faster or cannot maneuver. It cannot turn left or right very quickly. So you have to place the armor only in necessary location. You can't coat the entire aircraft with armor. You have to place it only in some places. So where do we place them was a question that came up. And in the British Air Force, a few set of scientists went to study. And what did they do? They looked at all the aircrafts that came from after going to the enemy territory, going to their raid, and coming back from the raid, they studied all the bullet holes on the aircrafts, and they say that these are the places where we see the bullet holes. So some aircrafts are getting hit on the wings, or the proportion of bullet holes on the wings is so much, the proportion of bullet holes on the tails is so much, and so on. So based on this, they decided to place the armor. So if you look at this image, where would you suggest placing the armor? If I give you a few names. So this is called the tail, these are called the wings, and this is the chassis or the frame of the aircraft, and these are the engines of the aircraft, and this is the nose of the aircraft. So if you look at this image, you may be tempted to put the armor in places where you find more bullet holes. So there are more holes here, there are more holes here. Let me put here, or there is higher density of holes here. Let me put the armor somewhere here. This is what a typical inference would be. And then if you go and look at how many bullet holes are there per square feet, you see this. And the tendency would be to put the bullet armor at a place where there are higher number of bullet holes, say in the fuselage or rest of the plane. So these are what you see. But one thing that is missing is that one thing that you don't really see is there are no bullet holes on the engines. The engines are relatively safe. Now, if you look at this, what is an inference that we draw? Does it mean that the engines do not get hit? No, because the aircraft guns fire randomly and the bullets have a chance of hitting anywhere. But what we don't see is that the aircrafts whose engines were shot did not return back to the base. So if the country sent out 100 aircrafts, say some 70 would return after a raid, 30 would not return, and they went and only looked at the 70 that returned and they ignored the 30 that did not return. The 30 that did not return had bullet piercings on their engines, the engines failed and the aircrafts failed, they did not return. That is a typical case of missing data. Something that is not there in your observations will lead to a bias in your observation, saying that okay, this is where we should put the armor. So this is a very classical example of missing data and the bias that comes in when we don't really realize what is the missing data. This is a typical EDA exercise that you will need to do. Other examples of missing data are this. Going back to the house prices example, some places you don't see numbers. So what do we do? This is a less riskier than the aircraft, but you have to do something with the missing data. So what do we do about missing data, or what are the mechanisms for missing data? We will see. So there are three typical processes for the missing data. The first method is what is called as missing completely at random. The data is missing, but it is a random thing. The second thing is missing not at random, and the last one is missing at random. We will see what each one of these are. So let us think of a study that returns age and IQ score for people. It will measure the age of the person and it will return the IQ score for the person. So this is the complete data set. And then this is the incomplete data set with missing values. So this is a case of missing completely at random. Why is it missing completely at random? We will see. So IQ scores are missing, but they don't have any dependency on the age. IQ scores are missing at different ages. It is not that IQ scores are missing only for younger people or IQ scores are missing for older people. IQ scores are missing for some young people also and for some old people also. So there is no dependency on age for the missing value. That is the first observation. The second observation is IQ scores are missing at different are present for different ranges. Higher IQ scores are there, lower IQ scores are also there. So there is nothing about IQ score itself to be present or not present. So there is no dependency on age, there is no dependency on the measured value, which is the IQ score itself. So with these two, what you see that this is a case of data which is missing completely at random. Another example is missing at random where IQ scores are missing. There are high scores present, low scores present, but they are missing for a particular age group. This mechanism is called missing at random, meaning it is just like our the aircraft example where we don't see bullet holes on the engine. Similarly, for low age group, there is no IQ score, meaning you did not really measure IQ for younger people. So this is the second case. You need to be cautious when you try to build a model for something like this because there is a bias in the model. We did not have IQ scores for young people. This is a bias that is there in the model. And the last set is missing at random, where the missing values are not dependent on the age. It is not dependent on the independent variable, but the low scores are missing. All the IQ scores you see are only high scores. So this is also a typical case where it is missing only for the low score people. It also will lead to any problem in the any. It will also lead to an error in the model if you try to model it anyway. So this is another thing that you need to be aware of. So we have mechanisms to identify whether it is MCAR or not. We can only tell whether the missing data is completely at random or not. We cannot really identify whether it is missing at random or missing not at random. So what do we do when we have to deal with missing data? The simplest thing is to delete the observations which are missing data. The second approach is to do imputations. Then there are other advanced approaches like using models or full maximum likelihood estimates. So traditional approach, I'll maybe go slightly faster to make sure we cover everything. Traditional approaches is about missing the deleting the observation. Delete all the observations which are missing values. Don't worry. Second approach is let me do a full likelihood estimate. There is a missing value. I will not really delete it. I will use it to make an estimate using whatever is missing, whatever is present. Then we will go to the second approach, second problem of outlier detection. So some data will have values which are outliers. Suppose you are measuring temperature in a particular town. All the ranges of temperatures are within say 27 to 35 degrees. Suddenly you see a 50 degrees value. So suddenly temperature being 50 degrees on a particular day, when the previous days and all the coming days are all in the range of 27 to 35. Is that a correct measurement? So that is a typical example of what is called as an outlier. So outliers are basically observations that deviate so much from our other observations, which will give you a feeling that they are actually either false or they are generated by another mechanism. So outliers may occur due to variability of measurements or experimental errors, or if there are heavy-tailed distributions and all, outliers may occur. So what happens in a normal distribution? If everything is perfect, in every 22 observations, you will see one observation which is an outlier. That is normal. It will be 2 standard deviations away from the mean value. If you take 1000 observations, 5 or more may be away, 3 sigma away from the mean value. Meaning, if you take 1000 temperatures, one temperature measurement may be slightly away from the 3 sigma value of that you see. But if in a set of 100 observations you see 3 outliers, that is a cause for concern. There is some problem there. You have to be very cautious or careful about that set of readings. So what do we do, or what methods do we use for outlier detection? If it is univariate data that is only of single variable, we will look at box plots or Z-score. If it is multivariate data, we will see multivariate Gaussian, dB scan, and linear modeling. We will briefly look at all these techniques. So univariate data is only single measurement, like we are thinking of the temperature. I am only measuring temperature in a particular town every day for the last 2 years. What do? We can look at the temperature values. We can do quantiles on them. What is 50th quantile? What is 75th quantile? What is 25th quantile? 95th quantile, 99th quantile, and so on. And anything about the 99th quantile or somewhere will be deemed as an outlier. So typically a 2-key box plot is what it is called. The middle line will represent the median value. The lower box is 25. The lower boundary is 25th percentile. Highest upper boundary is 75th percentile. And then 1.5 times interquartile range. Interquartile range is the difference between third quarter and the first quantile. So 1.5 times of that is treated as the inner fence, and then one more 1.5 is treated as outer fence, and anything above that is an outlier. And what is in between inner fence and outer fence is a suspected outlier, although we don't know for sure. Then other approach is what is called as a Z-score. You simply go and look at the mean value and see how many standard deviations is a particular observation away from the mean value. So Z-score is simply the given observation minus the mean by the standard deviation. It will tell you whether it is 2 sigma away or 3 sigma away from the mean value. So this is what we were referring to in the previous talk. So what do? For cases of multivariate data, I have 2 readings X and Y. Can I identify if any reading is an outlier? What do? We use what is called as a multivariate Gaussian to identify the outliers, and use this outlier and use this approach to throw away values which are seemingly faulty. So in this case, what do? In the case of multivariate Gaussian, X value may be within the 2 sigma range, Y value also may be within the 2 sigma range, but the 2 values put together will give you an outlier. So there is something called as an elliptic envelope which will help you do this. We will talk more about it in the next lecture. Then other approach is what is called as dB scan, density based spatial clustering of application. It will help you identify points which are close to each other and then help you identify probable outliers. So this is one algorithm or one tool that people use when they want to detect outliers. The last approach, the other approach is what is called as linear modeling. Instead of doing all these outlier detection techniques, I will build a simple model. I will try to predict a missing value, and if the or I'll try to predict a particular value. If the error between the true value and the predicted value is very high, I will call this an outlier. So let us say there are two values x and y, and I want to predict outliers in y. Let me build a simple linear regression of y as a function of x. So y is equal to some mx plus c. We will build a model and we will try to predict. And y true minus y predicted, we will see. For all the predictions that we make, we will measure the y true minus y predicted. And if that is very, very off, we know that y is the outlier value. This is the linear modeling approach. Another approach is isolation forest. People build random forests to isolate the outliers, and outliers will get eliminated in the higher branches of the tree itself. They are not, or they won't hold until the end branches of the tree. But are all outliers to be discarded if everything an outlier? There is something called as a king effect, which is outliers, all outliers are not wrong. You think of this example, this is an example of the country's population rise to the power of 0.42. So there is a country population rank on the x-axis and the population to the power of 0.42 on the y-axis. You will see that all the countries around the world fall onto a line, but there are two countries in the world which do not fall, China and India. So if you don't know the country names, you tend to discard them, but then they are actually true. That is present, it is true. These are called as outliers, but this is called as king effect. You cannot simply throw away all the outliers. Then the last thing that you go to do in EDA is dimensionality reduction. So data will usually come with large number of features, because any company or any measurement device would measure as many things as it can measure. So you will have 20 or 30 features about a customer who comes to your supermarket for purchase. Do I use all the 20 or 30 features to build a model? We may not. So we have to, what do we need to do? We need to do what is called as dimensionality reduction. What is this? We will see. So dimensionality reduction is about selecting relevant features for your model, what will help your model to perform well. And there are two approaches to do dimensionality reduction. One class is called feature selection and the other class is called feature projection. So what are these two? We will see. So feature selection will try to find out a subset of original variables. Let us say I have 20 features for a house to predict the price of the house. Feature selection will try to identify the top 3 or 4 features which will help us in identifying or predicting the price of the house. So this is called as feature selection. It will do filtering either based on correlations of features. It will throw away some features which are correlated, and then it will try to build a model. So feature selection approach is computationally effective. It will do an answer quickly. It is also robust to overfitting. And then there are another class of approaches called as wrapper methods, which will evaluate subsets of variables. If I have 20 variables, I will take 3 at a time, 4 at a time, 5 at a time, and so on, and then build a model. It will take a long time to build a model, and there is also a risk of overfitting the model. And then there are other methods called as embedded methods, which will combine both the filtering and the wrapper things. There is always a hybrid approach, which will take the best of both worlds. And then the other class of approaches to solve dimensionality problems is feature projection. So what do we do in feature projection? In feature projection, we transform the data into a low dimensional space, meaning that if you have 20 features, we will try to transform the data into a low dimensional space of 5 or 10 features. So some of these you may have heard already. Principal component analysis, you may be familiar with that. And then there are non-linear transformation approaches also, like kernel PCR, TSNE. Then we do non-negative matrix factorization that we also saw in the recommendation engine context. Then there are graph-based approaches like LDA, GDA, and all. So what will we do? So simple, some of the simple techniques are mentioned here. We do linear transformations on the data. So if you look at this data set, there is variation in the x coordinate. There is also variation in the y coordinate. But you see that if you rotate this data set into 2 different axes, the variation in the y coordinate will become very small, which is the linear transformation that we do. So let us say we choose 2 new axes, where the new x-axis is the cyan arrow and the new y-axis is the purple arrow. You realize that highest variation is only in the dimension of the new x-axis and not in the dimension of the new y-axis. So new x-axis can be used to predict the required dependent variable, ignoring the new y-axis. So this way we can reduce the features of the data set. And another approach of nonlinear transformations is what you see here. So there is a Swiss roll kind of data. We do an unrolled manifold, it becomes flat. Or we do a recovery by LLE, it becomes something like this. These are nonlinear transformations. So they operate on the data to transform them into simple low dimensional spaces. So this is an example of dimensionality reduction. And another example of dimensionality reduction or another approach is to use encoders. So encoders are simple neural networks which will compress the data to a lower dimension and then regenerate the data from the lower dimension. So if you given 10 numbers as an input, there is a neural network which will reduce the 10 numbers to say 3 numbers, and then from the 3 numbers it will regenerate the 10 numbers again. So this is called as an auto encoder. It will do encoding and it will do decoding. So the a high dimension is reduced to a lower dimensional space, and then it is reconstructed back into the original high dimensional space. So encoders will help us to identify outliers or identify anomalies. How do they do? Basically, any given value of x, it will construct a low dimensional representation and then reconstruct. If the error between x and x prime is very large, that is an outlier or a typical problem. And what is the basic building blocks of the encoders? We have a neuron, which is what you see here. A neuron will have a set of inputs x1 to xn. We learn some weights by training the neural network. We sum the weighted values wi into xi. We sum them, and then it undergoes an activation function and gives out an output. And the activation function are usually typical value. And the neural network is a collection of such neurons. So what you see on the top right block, top right image, is one circle here. This is one neuron which will do all this. It will take a lot of inputs, do something, do a calculation on this, and then give out a value to the next neuron. So neural networks are used in auto encoders to reduce the dimensionality of the data. So this is how they typically look or they do. And regularized autoencoders, sparse autoencoders, denoising autoencoders, all these are different types of autoencoders that are used for various applications. You want to denoise visual data, we use something. You want to denoise what do you call say spoken text data, you do something else. So these are all various variants of those which are called as autoencoders. And these are some examples where it will split and autoencode dimensionality reduction by splitting. So this is called as a variational autoencoder, which will have two splits: one latent variable model and a existing physics, the evident variable model. All these are examples, and with this we come to the end of a simple summary of EDA. Maybe there are any questions on this also I can take. Maybe
Participants, any questions? Hello.
Yeah.
Participants, if you have any questions, you can ask now. Sir, you can proceed, sir.
Yeah. Okay. So basically, this is all I had on the EDA part. Maybe next class I'll come with some preparation. I'll get content for 2.5 hours so that we'll have a.
Okay.
Yeah. If you have any other questions also, please feel free to ask, sir. No problem.
Sir, can you please explain a little bit that how optimization techniques can be implemented on a recommended system?
Okay. Can you tell me something more about the context, madam? Optimization of a recommendation, right?
Techniques like PSO or I mean Kuko search or any nature-based algorithm.
Okay, so you want the context of optimization in a recommendation system, as far as I know, will come from. I know it only in the retail world, madam. What is applied to retail businesses? So let us say we send some recommendations to a particular customer, and the customer picks up those recommendations. That will have an effect on the other products. So there is something called as cannibalization. You promote one product, the sales of another product will go down. That is called as cannibalization. Or people will tend to buy more when there is a promotion. So in that context, I know of optimization, madam. I am not really familiar with what you are asking. Is that what you are referring to, or something else?
Yes, sir. How optimizedly or how optimizedly we can recommend the product? Fine.
Okay, by optimally recommending the product, then yeah, then it will go to that example only, madam. So when we are recommending a product, what we do is we also look at the data to identify what are the typical complements and substitutes for that particular product. Let us say you are a retail store, you want to promote one particular product. You also have to look at what effect will this product have on other items in my store. So let us say one example would be like say Horlicks, Complan, Boost, and Bournvita kind of a thing. And you are promoting Horlicks for some reason, people tend to buy more of Horlicks. The Complan sales will get affected. So from there, people try to understand all, and from there we are try to build models to see what is the level of discount or promotion that we need to give, or for how long should we run the promotion. So there we use thing. I mean, we have used optimizers in Python in something like Pulp. We have used to decide what is our some other tool called Gurobi. These are optimization tools available in Python. We work in them to what do you call to decide on the kind of schedules or optimize to promotion schedules to run for retail stores. So we need to for optimization, we need to have an objective function. We have to look at what is the function that we want. We want to maximize revenue or maximize the margin for the retailer or maximize the number of items sold. So based on that, we can formulate the problem and see if I am recommending something, do I recommend it at some price point or do I recommend it for these many people? That kind of things can be cast as an objective function, madam. I hope that gives some answer. Now, may not be the exact one that you are looking for, but
Okay, sir. Thank you, sir.
Sir, can we conclude the session, sir?
yeah, sure, no problem.
Okay, sir. Madam, Sumaparthi, madam.
Yeah, sir. So thank you, sir, for helping us to become more aware of machine learning on large data sets. Uh, so I would like to thank behalf of Department of IT of Sri Vishnu Engineering College for Women for taking part in our 2-week FDP data science using Python. Your talk on the topics like dimensionality reduction, missing data mechanisms, recommendation systems, these are all quite interesting and informative, sir. So I strongly believe that whatever content or knowledge you share with us will help definitely in development of the research and academic career. So we know that your time is very precious, and we are grateful that you share some of it with us. We look forward to your participation in our future events. Thank you once again, sir.
Yeah, thank you very much.
So if any,
Thank you, sir.
if any participants wants to share their views or give the feedback, you can go ahead. If anybody wants to share.
Participants, if you want to ask anything, you can ask now. And if you want to give some feedback, you can give. Okay, sir, we can close the session. I think no one is
Yes, sir.
asking. Thank you very much, sir.
Yeah, thank you, sir.
Okay, sir.
Thank you, sir.
Okay, thank you, participant. Uh, uh, through WhatsApp, that is, we will send a feedback form and as well as attendance form. I request you to fill the feedback and attendance form before 6 o'clock. So the 6 o'clock, the feedback form response will be closed. Okay. So try to fill the feedback form before 6. So thank you very much. You can leave the session now. Thank you all.
Thank you, sir.